Hello students. So today our topic, that is electric potential energy of a dipole in a uniform electric field. So in this chapter we have to derive electric potential of a dipole which is placed in a uniform electric field. So in previous class, that is lecture number 3, we learn electric potential for a various various point charges, and here we have to calculate electric potential of a dipole and which is placed in a uniform electric field. So first of all, you have to know what is electric dipole, which is in chapter 1, you know, that is equal and opposite charges when there is a minus q and there is a plus q charge, and they are separated by a small separation, suppose 2a, so they form an electric dipole. And defining electric dipole, the strength of the indicating the strength of the electric dipole, we use electric dipole moment, which is represented by symbol P, that is formula Q into 2a, that is either charge into the separation between two dipoles, the separation between two charges, and here the dipole direction, the direction of dipole moment always negative to positive charge. So first of all, we have to consider an electric dipole, and this dipole will be placed in a uniform electric field. You know what is a uniform electric field? That is an electric field in a region where is a magnitude value, in particular region the magnitude value is same and the direction of electric field along a particular direction. So suppose there is a uniform electric field and a dipole, that is plus q and that is minus q, and separation, suppose this separation is 2a, okay, is placed the direction of uniform electric field, and it's making an angle theta with the uniform electric field. So here for plus q charge, there exerts an electrostatic force which is directed along the direction of electric field, and this force expression F, that is equal to q into E. And for minus q charge, there is another force which is directed F, that is equal to minus q into E. So there are two equal and opposite forces, and these two forces form a couple, and the torque exerted by this couple, what will be the expression of this torque? The expression of torque tau, that is, you know the formula, that is force into perpendicular distance. Clear? Now the magnitude value of force, that is q into E, and perpendicular distance, and this separation is 2a angle theta, so this component is 2a cos theta, and this component, that is 2a sin theta. So the perpendicular separation, the perpendicular distance between two charges, that is 2a cos sin theta, so that is 2a sin theta, and this expression will be q into 2a, which represent dipole moment P, that is P E sin theta, which is in chapter 1, that is P cross E. You know the formula, that is the torque exerted by this couple, which is made by two equal and opposite forces here. Now suppose this dipole rotating through an angular displacement d theta, that is anti-clockwise, against the direction of torque. You know the direction of torque, formula is P cross E, that is the cross product of P and E, clear, which is directed by the rules right hand thumb rule. So when this dipole is rotating through an angular displacement d theta against the torque, what we have to done? Work, and this amount of work, formula, what will be the formula? You know the formula, that is W is equal to F into X, force into displacement. But this formula is valid when force is constant. But when force is variable, what is the amount of work done? That is dW is equal to integration F into dx. Clear? Here F is variable. This is all about linear case. But for angular rotation, what is the formula for calculating work done? That is W is equal to torque into angular displacement. And this work done formula is also valid for when torque is constant. Here torque tau, the magnitude value, you see the magnitude value, if we write this is tau magnitude form, the torque tau magnitude value is depends upon theta. And what is theta? Theta is the angle between dipole moment and electric field. So here torque tau is a variable. So for variable torque, the amount of work done formula, that is tau into d theta, where d theta is the angular displacement. Okay, so the amount of work done in rotating the dipole, in rotating this dipole in the anti-clockwise direction, that is the opposite to the direction of torque, formula will be tau into d theta. Now putting the value, that is tau, that is Pe sin theta into d theta. This is the amount of work done. Clear? And this amount of work done for angular displacement d theta. Angular displacement. D theta represent angular displacement. Now suppose this dipole is rotating through an angular displacement, through an angle theta 1 with respect to the direction of electric field to theta 2. This dipole is rotating through an angle theta 1 with the direction of electric field to theta 2. What will be the total amount of work done? So what will be the total amount of work done? The total work done, that is integration total work done, that is W is equal to integration dW, that is integration theta 1 to theta 2 Pe sin theta d theta. Here Pe constant, so this one will be outside, that is Pe integration theta 1 to theta 2 sin theta d theta, that is Pe minus of cos theta, theta 1 to theta 2, integration of sin theta d theta, that is minus cos theta. Now putting the value, that is putting the limit, that is Pe minus cos theta 2 minus cos theta 2, then minus of minus, that is plus cos theta 1. So this result will be Pe cos theta 1 minus cos theta 2. This is the amount of work done, total amount of work done in rotating this dipole through an angle theta 1 to theta 2. Clear? Through an angle theta 1 to theta 2. And you know the relation, that is the amount of work done. This amount of work done is stored as a form of electric potential energy. So electric potential energy formula, that is Pe cos theta 1 minus cos theta 2. This is the general form. This is the general form of electric potential energy for rotating through an angle theta 1 to theta 2. Now suppose let theta 1 is equal to 90 degree. That means this dipole is placed perpendicular to this electric field, and then this dipole is rotating through an angle theta, that is here theta 2 is represent theta. Then what will be the expression of U, that is the potential energy? So simplify it, that is U Pe cos theta 1, that is 90 degree, minus cos theta 2, that is cos theta. Clear? That is expression will be PE, this is 0 minus cos theta, that is minus PE cos theta, which you can say the dot product of P into E. So the electric potential energy expression becomes the dot product of dipole moment and electric field. Clear? And you know the expression of torque, this one, the cross product of dipole moment and electric field. So the cross product of dipole moment and electric field is represent the torque, and the dot product of negative of dot product of dipole moment and electric field is called the electric potential energy. When first condition, that is the dipole is placed initially perpendicular to the electric field, after that the dipole is rotating through an angle theta. So this is the expression 1, this is another expression 2. Okay. Now there is some special case, there is some special condition. Okay, write it down. There is some special condition. That is, first of all you write the formula, after that write it the condition. Okay, so expression of torque tau, that is P into E, expression of U, that is PE cos theta 1 minus cos theta 2. After that we calculate U, that is minus P dot E. Clear? Okay. Now case number 1, special case number 1. Case number 1, that means suppose this is the direction of uniform electric field and the dipole is placed like that. This is minus q, this is a plus q, this is a electric field direction, and the dipole which is placed parallel to uniform electric field. So what is the angle between them? The angle between P vector and E vector, which is parallel, so 0 degree. So what will be the result, final result? You know the result, that is minus PE cos theta. Okay, first of all you calculate net force. What is the net force here? Net force result 0. Clear? Now net torque, that is torque expression P cross E, that means PE sin theta. So PE sin 0 degree, sin 0 value, that is 0. Now U is equal to minus PE cos 0, that is U is equal to minus PE. This energy, this potential energy is the minimum value, because the minimum value of cos theta, that is 1 or minus 1. Okay, that is U, that is minimum, is equal to PE cos theta. This condition is called stable equilibrium. This condition is called stable equilibrium, that is the system is in stable equilibrium. And when the system is in stable equilibrium, when the direction of dipole moment and the direction of electric field, that is parallel to each other. Clear? Okay. When if net is equal to 0, it indicates translational equilibrium. Translational equilibrium. When torque is equal to 0 for rotational case, so it's represent rotational equilibrium. That means if there is F equal to 0 and tau equal to 0, which indicates the system is in equilibrium, and here negative of energy, which indicates the system in stable equilibrium. Clear? Now case number 2. Case 2. Suppose the electric field like that, and the dipole is placed perpendicular to electric field. Okay, so what is the angle? Theta is equal to 90 degree. So here F net, that is also 0, torque tau, that is PE sin 90, that is 1. So here torque tau is equal to PE, that is the maximum value. Here torque tau is maximum value. And what is the value of U? That is minus PE cos 90 degree, cos 90 is 0, that is U is equal to 0. This is called position of zero energy. Here the energy of this system is equal to 0. So what is the significance of this zero energy? The significance of this zero energy, that means if we hold this dipole perpendicular to this electric field, and if it brings from infinity into this electric field, then the work done on the charge plus q, by the external agent is exactly equal to the work done on the charge minus q. That's why the net work done is 0. As a result, we can say the potential energy expression is 0. Clear? Now, final case, that is case number 3. Case 3, that is if the dipole is placed anti-parallel, here negative sign, negative of q, here it is positive of q, that is the dipole moment is directed along the negative direction of x-axis and electric field is directed along the positive direction of x-axis. Then what will be the expression? Okay, F net for every cases, that is 0, torque tau, that is PE sin theta is 180 here, here theta 90, here theta is equal to 180. So sin 180 result, that is also 0. So this is the expression of minimum torque. This is also expression of minimum torque. Clear? Now U, that is U is equal to minus PE cos 180, and cos 180 value minus 1, that is minus PE minus 1, that is plus PE. So this expression, this potential energy is maximum value, and this potential energy condition is called unstable equilibrium. Unstable equilibrium. Clear? Okay, same thing, if F0 which indicates translational equilibrium, if torque tau 0 which indicates rotational equilibrium, that means F0 torque 0 which indicates the system in equilibrium, but here sign positive which indicates the system in unstable condition. Clear? So there are 3 cases. There is if theta is equal to 0 degree, that is F and E are parallel to each other, in that condition the torque the system in stable equilibrium. When theta is equal to 90 degree, that is electric field and dipole moment parallel perpendicular to each other, in that case that is the position of zero energy. And when electric dipole moment and electric field anti-parallel to each other, that is theta is equal to 180 degree, in that condition the electric potential energy is unstable equilibrium. So this is an important part, that is the electric potential energy of a dipole when it is placed in a uniform electric field. It is important for your exam, board exam. Okay, so this is all about this lecture. This is the potential energy formula when dipole placed in a uniform electric field. So stay tuned, next lecture will be coming soon. Thank you.